because I rebooted the computer. Alright, so let's see how the internet works. Yay. Alright, so I'm going to do the quiz first, and then we'll take questions, and then we'll move on. So let me work the quiz real quick. If you want to. I don't care. Whatever you want. That's distracting. Alright, so here's the quiz. And so what was the point of saying that changing the 1.3 volt source to 1.15? What?
So it satisfies the parameters in the table.
Yeah, so it satisfies the parameters in the table, but it's a long channel process, right?
Yeah.
Yeah, and then what was the idea with changing it to 32? Same thing, right? So then I can go like this and go GM equals 150 microamps per volt squared. Then I know that I'm going to draw the AC schematic and tell me if this doesn't make sense. Why did I replace the VDD with ground? It's AC ground. I can't change that DC voltage, right? And then I'm going to draw my source here, 1 millivolt. It also goes to ground, so I could have drawn it the other way going to ground, but it's source to gate voltage looks like this, and so this is GMVGSG, which is 150 microamps per volt squared times 1 millivolt, so ID equals 150 nanoamps. Boom, I'm done. Don't try to trick you. I'm like looking at those quizzes, I'm like, holy crap, they're making it hard. Any questions? Yes?
Outside of the quiz.
Yep. Oh yeah, are there any questions on the quiz? Okay, are there any questions on anything else?
You know what we talked earlier, and when you have, when you're doing a DC analysis on NetMoss, let's say, right? So you want to do, you just want to check, you want to test for VDS. Let's say you want to just do, can you just do VDS equals current times the R channel, if the R channel is obviously in trial? I mean, the NMOS is in trial too.
So you're asking if I have a device like this, and it's whatever, it's in triode, so it's R channel, and then you have a current here, ID. So wait, does this equation GMVSG work for triode? No, I'm just asking. I'm not saying you said that. It doesn't, right? And then now, you know, the ID goes through here, then yeah, that voltage is ID times R channel. Looking good? What do we have for lunch? Jason's Deli? Pretty tasty, man. I had cottage cheese. Curds and whey. There you go. Did you guys know that's what curds and whey was? Yeah, okay. The watery stuff's the whey, and then the curds is the, yeah. All right, any other questions on anything? So let me do an example now. Just before we move on, I want to do an example where I feel pain and do a quadratic equation. Students like it when you feel pain, don't they? So where's Cassandra? Oh, she's not here. Okay. All right. Just checking. I got to mention people's name when they don't show up. So, you know, in 15 minutes, we're going to be mentioning some other people. Aaron. Yeah, then they're going to be like, ah. All right, so let's just do this. 100K. And then let's do 50 by 2. And then let's go over here. Are they staring at us as they come by? And let's say this is 50 by 2. And let's say this is 50K plus 5 volts, plus 5 volts. And I want you to calculate all the voltages and currents in the circuit. Seem like a good quiz question? And when are we meeting? The next time we meet after today? Next Friday, yeah. Yeah, 5 volts. 1 micron process. Tell me what to do. So the 1 micron process, let's just write down some simple stuff. Threshold voltage 0.8, Kp sub n is so tell me what to do. So ID is what's that equal to? Keep me honest, man. Is everybody cool with that? So here I've got 60 times 25. Then I'm going to take this bead and slide it up, and that'll be times 100K. And should I get my calculator out, or can I trust someone to calculate? And Lito, you're going to be calculating? All right. So what's that equal to? So this is 60 micro times 25 times 100K. $150? All right. So 150 times VGS squared minus 1.6 VGS plus 0.64 equals 5 minus VGS. Looking good? Or 150 VGS. I'm doing this because when we have these on the tests and the students are like, oh, that was a lot of calculations, I'm going to show you it's not that bad, okay? And what's 1.6 times 150? 240? And then what's 150 times 0.8? 120? Yay. I like it. Oh, whoops, I don't want that. I want 150 times 0.64. So that'd be 64 plus 32, 96. Yeah. Is everybody cool? And then I go over here and I write that 150 VGS squared minus 239 VGS plus 91 equals 0. And I'm going to label this 3, and I'm going to label this one 2. Is everybody cool with that? Now what? Why don't we... Alright, I'll just write it. So many ways I can do it. I can divide through by 150, or I could just use the equation. So let's just say VGS equals the opposite of B, 239, plus or minus the square root of B squared, which is 239 squared minus 4 times A times C divided by 2A, or 300. And let me do a quick little calculation here. What's that? 0.964. What's the other root? I asked, why is this one right last time? Tell me in simple terms. Why is this one right and this one wrong? Yeah, less than the threshold voltage. Yes?
Just curious on that one. If you do have less than a threshold, less than the threshold, is that like, you bias up like that? Does that make sense?
Well, there's some circuits that operate at sub-threshold, like your calculators and your wristwatch and all that, and people do bias at those voltages, but there's challenges with matching, because if you have slight variations in the threshold voltage, you can have significant variations in the current, because in the sub-threshold region, the current is exponentially dependent on VGS. It's not a square law like in the strong inversion. So what we're doing, we're not going to do any sub-threshold stuff here because there's practical issues with it. What if we had roots of 0.964 and 5.23, which would be right? Why? Can't be greater than the power supply voltage. Is everybody cool with that? Okay, so now that gives me what? What do I do next? Okay, tell me the easy way to calculate current. So I just found out this was 0.964. Yeah, just 5 minus 0.964 over 100K. Don't plug it back in the square law equation. That's a little bit more calculate. I mean, you'll get the same answer. It's just more work. So we say, oh, ID equals 5 minus 0.964 over 100K, which is 4.036 over 100K, which is 40.36 microamps. So I get 40.36 microamps. So this is a current mirror. What's the current flowing in here? Now I'm neglecting output resistance. For same thing, right? Okay, so am I done? No, I need this voltage right here, right? What is it? Okay, so everybody is cool with saying it's 5 minus 40.36 times 50K, which this was 100K, this was 50K, same current. What's going to be the voltage drop from here to here? Half of that. So 0.45 plus 0.32 is 0.482. Is everybody okay with that? So then what's the answer though? Because if you do that, you'll lose a point. What's the answer? .518 volts. What was, did I do that right? No, I made a mistake somewhere. What did I do wrong? I did something wrong. I said, oh, this voltage is 0.964. The voltage drop across here is 4.036 volts. What I did was wrong. I said, oh, the voltage drop from here to here is half of 0.964. That's wrong. It's half of 2.036. So the voltage drop, did everybody see the mistake I made? Sergio? So what I did was I said, okay, I calculated the VGS as 0.964. And I said, oh, well, the voltage drop here is 0.9, half of that, because this is 50K and it's 100, and it's not. It's half of the voltage drop across here. But the voltage drop across here is 5 minus 0.964, or 4.036. Does everybody follow that? And so I take that, and the voltage then across here would be, so this is wrong. So let me draw it neat, just because it's getting, I'm not drawing it nice. Having nightmares of grading your homework. So let's do it right. What's the current through here? What's the current through here? What's the voltage drop here? What's the voltage drop from here to here? What's the voltage drop from here to here? What's the voltage there? (982) if I did the math right. Yay? Would this be a reasonable test or a quiz problem when we come back on Tuesday the 23rd? All right. Any questions? So let's start talking about how we make a reference that is, how do we make a current reference? So this next part is pretty important in the class because we're going to be using this circuit over and over again. And I want to just give you some motivation for why we're going this route. So if I take and I just use a resistor and I make a current mirror that looks like this. If I think of this circuit, this is equivalent to thinking of a current that looks like this, right? So this point and this point are the same. Does everybody understand? So in a real circuit, I can make transistors, I can make resistors. That's how I model and make a current sink. Does everybody follow? The problem is, what happens if I start varying VDD? We know this current that flows through here is VDD minus VSG all over R. Is everybody all right with that? Well, if I vary VDD, what happens? The current's going to change. Well, that's not a constant current, is it? I don't want variations in VDD. I don't want to be listening on my cell phone and have the battery drop in voltage and it get quieter or not have as large a signal. Okay? So what I want to do is I want to try to make a reference that isn't dependent on VDD. Now you could argue, well, what if I do something like this? I make this a long L device so we get a large voltage drop. And then I do the same thing. And then once again, I have this. And so we have the same exact problem. It's dependent on VDD. And notice that here we have the resistance in the drain part. Here we have the long L device in the drain part. So what we're going to do is we're going to put the resistance in the source part. And I'm going to show you the motivation behind this. This circuit's going to use positive feedback. You might have thought positive feedback is bad, and it can be, but if you use positive feedback with a gain less than 1, so the loop gain is less than 1, you can make a stable circuit. If you have positive feedback like a speaker with a microphone and your gain's greater than 1, you get that screeching sound, right? But if you have negative 1, you'll just get an echo and then it dies out, okay? So consider the following. And we'll do some sims with this as well. What I'm going to do is I'm going to take and make my normal size devices. Let's go with, for the 1 micron process, the sizes we used were in the back of the book, 10 by 2. Now I'm going to make this so that I'm going to design this reference so there's 20 microamps flowing in it. This is what I'm going to use to generate a constant current in my analog circuits. And this is what I'm going to use. I'm going to replace with a current source. So all those things where you learned in circuits, where you had a current source, this is actually how you make them. So I'm going to come over here now, and I'm going to put a resistor in this side of the circuit. The problem is, if I make, this is a current mirror, but if I make this size, these two sizes the same, then the VGSs would have to be the same if I have the same currents flowing through each side, correct? Well, if they have the same VGSs, what's left to drop across the resistor? Nothing, right? So you don't get any current flowing in there. So what I'm going to do to get around that problem is I'm going to multiply up the beta of this guy by increasing the width. I'm going to make it, say, 40 by 2. Or in other words, I'm going to make it K times W over L, where this W over L are the W over L that I've selected in my analog design based upon speed and gain and all that stuff from chapter 9. Okay, everybody follow that? So now I'm going to write this as I'm going to call this M1. I'm going to call this VGS1. And I'm going to call this VGS2. And I'm going to try to force the same current through each side. What's the simple way to force the same current through each side of this circuit? If I want the same current flowing through both sides, what do I do? What's that? No. How do I get the same current flowing through each side? Can't put a resistor here because then I have the same old problems, right? Because then I'm sensitive to VDD. Yeah, PMOS current source. So I'm going to go over here. And I'm going to put a current mirror just like this. So now, if I design this right and I get 20 microamps flowing through this, it mirrors over here and I get 20 microamps flowing through this. But I'm going to just leave it as I ref for now, and then we'll derive the general equations, and I'll label this as W over L. Now these sizes I want to be the same. I'll set them to my PMOS size, okay? So now, I'm going to ask you this at some point in the semester to derive, on some quiz, derive the equations governing the operation of the beta multiplier reference. This is a current reference. If we design it right, it'll generate a current that's independent of VDD. So if VDD is 3 volts, we get the same current, relatively the same current as if 5 volts. Okay? So, what can I say about the size of, if they have the same current flowing through each side, what can I say about the size of VGS1 relative to the size of VGS2? Same current, so what is the size of VGS1 relative to the size of VGS2, knowing this transistor is wider? Well, it's not going to be 4 times, remember, because the VGS is in the square. But the VGS2 is going to be less than the VGS1. Does everybody see that? If I make this device wider and I keep the same amount of current flowing through, the VGS is going to drop. So if I ask, now I'm going to ask trivial questions here. What is this voltage here? Does everybody agree with that? But what is this voltage here in terms of VGS1 and VGS2? Yep. Does everybody agree with that? So if I ask, what's this reference current? Tell me what it is. VGS1 minus VGS2 over R. Does everybody see no current flows this way? And no current flows this way. So the current that flows through here is independent, is not going to flow over in this side. Does everybody follow that? So would you be okay if I wrote VGS1 minus VGS2 over R? And now if I ask you, why does this have to have the beta multiplier up? Because then the VGS's, these are the same size, the VGS's are the same. This goes to 0, my reference current goes to 0, and that's worthless. Does everybody follow that? Okay, so tell me what to do now. Here, I'll start you out. Iref is equal to Kp sub n over 2 W over L VGS1 minus V threshold n squared. So I can write VGS1 is equal to the square root of 2 Iref times Kp W over L plus V threshold N. Would everybody agree with that? Okay, but how would I write VGS2 then? Yay? Only difference is I multiply the W over L by K. Is everybody okay with that? So far, so good? Okay, when I take the difference of VGS1 with VGS2, what happens to the threshold voltages? They cancel, right? Now, so I could write Iref, I'm going to do a little trickery here, is equal to the square root of 2Iref divided by Kp times W over L times R squared minus the square root of 2Iref over Kp times K times W over L times R squared. So all I did, I just squared this and put it in the square root, so it's 1 over R. Is everybody okay with that? So I'm making this look really easy. When you have to do it on the quiz, it's a little bit more challenging. So tell me what to do now. How about I take the square root, I cancel that like that. So I divide both sides by square root of Iref. Does everybody agree with that? Would everybody agree then I could also write the following? Is everybody cool with that? So I'm going to write this on the next page, and then we'll talk about it and do some sims. But before I do that, I'm going to square both sides. And then I'm going to write Iref is equal to 2 over Kp times W over L times R squared times 1 minus the square root of 1 over K, whoops, squared. Yay? Oh, we got so much here that we need to make sure we understand. So this is the basic equation. So let's say K equals 4. Tell me what happens. Well, yeah, the bigger it is, the higher the current, but I mean, how do I simplify this equation? So 1 over 4 is 1 over the square root of 1/4 is 1/2. And then it's 1 minus 1/2 squared, which ends up giving me what? The 2's cancel. Am I losing anybody on the algebra? I don't have to pick 4. I did here just because I get a good result. It cancels out the 2 and I move it over. Any questions? Because we're going to design a beta multiplier here that we're going to use. But before I do that, look at the following. Would everybody be okay if I moved this bead up here and wrote r squared is equal to, or actually let's move these up. Let's write it as 2kpw over L times I ref is equal to 1 over r squared. Taking the square root of both sides, I get 2kp times w over L times I ref is equal to 1 over r. Why is that interesting? This is GM. So I can set GM by just using the resistor value there if I set K equal to 4. Tricky, eh? So this is also called a constant GM bias circuit. Well, of course, if the current's constant, you run it through a transistor at a particular size, you're going to have a constant GM. Okay? Questions?
So we're going to, on a quiz, we're going to want to derivate that, or we're going to want to just say K equals 4?
Yeah, this is probably what I would ask for. I got a question. If K is really big, this term goes to 0. What's the issue with using really big K? What's that? Well, if you use really big K, the M2, that VGS goes to the threshold voltage. I'm not sure that's bad, but it is what it is, all right? So let's look at the back of the book, the table 9.1, and let's sketch the sizes. We have our basic size is 10 by 2, and that's diode connected. That's what we reference. And then over here, we're going to use this as a 40 by 2. Then for our PMOS, we're going to call these 30 by 2, 30 by 2. And then I'm going to put a resistor here of 1 over GM, but looking in the back, GM was 150 microamps per volt squared. 1 over GM would be 6.5 K. Is everybody all right with that? So what should the current flow according to the table in the back of the book? How much current should flow? 20. Okay, so I'm going to simulate this now to show that it's self-biased. Does anybody have any questions on how I got the schematic? I'm going to simulate it. I'm going to vary VDD. We're going to look at the behavior. Okay? Questions? Yeah. VGS1 minus VGS2?
Yeah, it's on the 40 to 2.
Oh, this one?
Yeah, I'm just missing where that's coming from.
So this is VGS. Then I get a voltage drop of VGS2. So this is VGS1 minus VGS2. No, you thought I was magic. I was doing magic. When I took classes, I'm like, that professor know what he's talking about. Is that magic? Because it wasn't clear. Oops, did I say that? All right. I'm sure you've never had that experience.
I have a question for you.
Yep.
When you have the 1 over R equals to GM.
Yep.
So R is our channel then?
No. R is this R right here. Through R we put in the beta multiplier. So I'm going to go through this now and sim it. We're going to see that it works because this is how we're going to generate our current source, and I'm going to show you how to use it. Okay? So let's go back. And let's pull this up. Yeah. I don't know what. Maybe if I uninstall it and reinstall it. Save as lec9. Save. Boom. So Co, what do you think we... Oh wait, Co's not here, is he? Oh, okay. All right. I gotta have my fun. All right, so I'm going to go over here and change this to 30. I gotta motivate people to show up. It's not that bad. Parking's good on Friday afternoon. It's in a good room. Second floor parking. All right. So this was 6.5K. And what is 1 over 6.5K equal to? 150 micro. We'll find out. And let's see, we got 5 volts there. We got our dot include. We're gonna grab the this thing here. Then I'm going to one more time get my NMOS 4. What kills me is the students go, well, I didn't know that's how you do it. And I'm like, how many times did I do that?
Can you copy paste it on my home file?
Yeah, let's do that. Let me show you how to do it. Oh, that looks nice. So you go like this, and then you grab that, and then you go over here, and if it's, you have to leave both open. You can't do Control-C, Control-V. So then you do a Control-E, and then you close it, and if it doesn't show up when you go over, like if you have a dialogue open or whatever, you have to exit out of the dialogue and or hit escape and then copy it. So, all right. I think this tool's pretty easy to use, don't you guys? LT Spice. I mean, it's awesome. Okay, Control E. One thing though that I think I'm gonna do, it's a little bit trivial, but I'm gonna do it anyway, is move the source so that it's in the right position. You see the source is this node, it's the one, the gate is closest to the source. So the source is here. So when you look at, if you look at the net list and you see drain gate source, it lines up correctly. Yeah, so this is the gate. And so source and drain are interchangeable, so everything still works. It's just nicer when, yeah, it's just nicer when you look at things if you see VSG and it's actually, this is the source and they don't have them flipped. It gets confusing. I don't want you to say I'm confusing. You know, you may say that anyway. All right. There's an issue that we need to talk about, and I'll talk about it briefly, and then we'll fix the problem, but and we'll talk about it more in detail. So let's go grab this one. And that is, there's two operating points. There's the one that we want, and then there's the undesired one where zero current flows. And I want to make sure we follow, oops, let's fix this. I can't have the two diode connected on this side, right? So I'm going to go grab, get my big hand here and move this. Then get this one, move this over. And I got to do one more thing. What's that? Should I use 40 or should I use M equal 4? Yeah, let's use M equal 4. All right. And the reason I do that is when you go into industry, especially if you go work nowadays in the smaller processes, they never will adjust the width. They'll always use parallel devices, and there's a couple of reasons for that. The main reason has to do with the printing of the devices. They're so damn small that when you start to change the size, you can't print them accurately. So they tend to use the same device over and over and just put them in parallel. Okay? All right, so any issues here?
Quick question now.
If there's more than in parallel, like, would the length increase? Or just-
No, the lengths don't increase. It's just think of it as 4 drains. I got a drain, 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 drain. You know, if I put them in series, then the lengths would go up. Questions?
So, because M4 is gate drain connected, we know it's in saturation. So, from that, we know that M3 is in saturation as well. Because there could be some instances where they're not both in saturation.
If VDD gets to be too small, then this guy will start to go into triode because the VDS isn't going to be large enough. And you'll see the current go to 0. So we'll see what happens when I run the sim, but one issue here is what happens if there's 0 current on this side and 0 current on this side? This node's at VDD, this node's at ground, and the circuit's happy. Hasn't started up. This node's at ground, this transistor's off, this transistor's off. If this node's at VDD, this transistor's off, this transistor's off. And that's fine, right? It'll work perfectly. So I'm going to hit run. And I'm going to go look at the voltages. And what was the voltage I expected here for VGS? And I'm going to allow you to look at the book that you've used this already. What is the VGS of M4? 1.05. Let's see what comes up when we designed it. 1.04257. Pretty close? What do I think the VSG of this transistor is? We just covered it right at the beginning of the lecture. I did the example. So what do I expect this voltage will be right there? 3.85. 5 minus 1.85, or 1.5, 1.15, so 3.85. Does everybody see that? Does everybody understand what's going on? If I go measure the current, what do I expect? $20 microamps. I'm only at 16. If I go over here, I'm at 15.5. That's off a little bit. Okay, because of the secondary effects, but it's still in the ballpark. Any questions? So I'm going to do another sim now, and then we're going to put in a startup circuit to ensure we don't have problems starting up. Any questions on this circuit? There's 2 what? Yeah. So let me come back to that. I want to do the sweep with VDD, then I'm going to come back to it. We're going to design a circuit to, I'm going to show you the problem in the transient, and then we're going to fix it. All right? So I'm going to close this. Then I'm going to do a file save as, and go to example 2. And then I'm going to do the following. I'm going to go here, and I'm going to do a .dc. And I'm going to sweep VDD from, let's say, 0 to 5 in 1 millivolt steps. So what I'm doing is I'm sweeping VDD from 0 to 5 in 1 millivolt steps. And what will happen is once I get above 1.15, plus the voltage I need here, which is roughly 0.25 for the VDS set, the 1.05 minus the threshold voltage, VGS minus V threshold. So once I get above roughly 1.6, and I'll cover this again in a moment, this is going to turn on and I'm going to get a constant current. Now I'm going to cover that minimum voltage one more time in a minute. So I hit run, and then I look and I plot the current, and I see that roughly here 1.3, that's a little bit lower than I was thinking. The current snaps on and I get a fairly constant current. Everybody follow that? So if I change VDD from 2 volts to 5 volts, the current stays relatively constant. I don't have a current that changes much. Okay, how do I use this? This is my reference. How do I use it? This is my reference source. I want to use it. I want to use it one of two ways. I can go, how do I make a current near here? Let's ask that. I connect to either this gate or this gate. Which do you want me to do? The PMOS or the NMOS? Let's use the NMOS. So I go over here, and I'm going to be fancy. And I'm going to get the scissors out here. And instead of drawing the wire over like this and making a connection, what I'm going to do instead is I'm going to go out here and I'm going to go V bias N. And I'm going to copy and say this node is labeled V bias N, as is that node. So if I simulate this, how much current flows in this device? The way it is right now. 0. Why? There's no source, right? So let's go up here. Do this. Now I'm going to run the sim. That's the same current I was plotting before. Now I'm going to plot this current. What do I expect? Is this current going to be the same, less, or more than the current through M3? And why? It's going to be basically the same, but it's going to be slightly larger. Why? It's got a larger drain to source voltage. So if I go over here and I plot that, see how the drain to source voltage, and they're precisely equal when this drain to source voltage is equal to this one's drain to source voltage. Notice if I right click on this node and I say highlight net, it tells me. You can go crazy in simulations if you have things labeled, like use some common name like N1 for node 1, and you're using it in several places. It means they're shorted together and you just can't tell. Does everybody follow this? Does everybody see how I would use this to generate a current? And I would think of this point as a current source, and then I would ask, VGS is 1.05. What's the minimum voltage I can have right here? It's in order for this to behave like a current source. What's the minimum voltage? If VGS is 1.05, what's the minimum voltage I need to keep this in saturation? Okay, since everybody's not screaming the answer, I'm going to do this. I'm going to make one more sim. And I'm going to save this as example 3. I'm going to get the scissors out here. Yeah. And I'm going to copy this. And I'm going to call this. We need to make sure that what we're covering right now, because you're going to use that over and over again in the class too. I'm going to put a source here. I'm going to call this source V out. And then I'm going to sweep. I'm going to just leave VDD at 5 volts, and I'm going to sweep V out from 0 to 5 in 1 millivolt steps. So when V out is 0, how much current flows in this device? None, right? Okay, so I want this to be in saturation. So if I go back over, and I do the following, here's my transistor. I've got a bias voltage there, V bias N. We know where that comes from, and it's 1.05. So what is VGS? If I want this device to stay in saturation, what do I have to require? And what's another name for that? Or overdrive? Okay, so this is 1.05. What's the threshold? So what do I need the voltage there to be? Greater than 0.25, right? Notice that's much smaller than the minimum VDD. Questions?
Did you say you're going to explain the minimum VDD again?
Yeah. Don't worry, man. And I also need to explain the startup. Okay, does everybody follow? So when I go run the sim now, when am I going to see this current go up to 16 microamps? Roughly 250 millivolts. So I'm going to hit run, I'm going to hit save, and I'm going to hit run, and I'm going to plot the current through here. There it is. Notice how it's nice and flat. Does everybody see it's going up? Does anybody have questions? Okay, so before I do the startup circuit, let's revisit the minimum VDD. Okay? Let's look at the minimum VDD. I'm going to do it 2 times. I'm going to just tell you, and then I'm going to draw a schematic, and we're going to write it down. What is the voltage, minimum voltage from here to here? Yeah, it's not going to work. I'm going to have to tell you. So if I have the transistor like this, and this voltage is 1.15, so this is 5 volts, and this is 3.85. For this device to be in saturation, VSD has to be greater than or equal to what? Does everybody agree? So the minimum voltage between here and here has to be 0.25. So the minimum voltage from here to here is 0.25. But what's this voltage here? VGS. It's 1.05. So when I add 0.25 plus 1.05, that means that it's going to turn on at 1.3 volts. So if I go back and I look, when does it turn on? 1.3 volts. So I'm going to do it one more time. This is another common question I ask. So here's our circuit. What's that voltage there? The minimum voltage I need there? Well, I mean in terms of VSD sat. It's VSD sat. What's the voltage here? VGS. So would you all agree that VDD has to be greater than VGS plus VSD sat? Does everybody agree with that? Or I could write that as V overdrive plus plus V threshold N plus VSG minus V threshold P. I mean, there's all kinds of different ways I could write it. But does everybody follow that? Any questions? So I'm going to do another sim. Look at the following. Let's see if I can make this break. And this, I will tell you, when you do design, the startup circuit is often neglected because once the circuit starts up and you're not in the state that you want to be, it doesn't do anything. So people tend to neglect it, and then when they get their silicon out of the fab and they test it, they find out, hey, this doesn't work. And then they have to fiddle with the power supply to flick it to get it to start up, and that's not good. So it's important that you spend time on this. Okay? You know what? What the heck's going on here? Let's... Alright, whatever. So let's go just grab this one. And I'm going to do a dot tran. And let's do, I'm going to try to make things break. Stop time 1 second. Now I'm going to hit run. Whoops, 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 whoops. What did I do? Save as example 5, was it? 4.
Oh, there's 4.
There was already a 4?
Yeah,
Ah, oh well. You're getting cheated. Alright, so I got dot tran there, run, and then I look at the current, and let's force it to fail. So let's call this node V bias N. Let's call this node V bias P. And then let's go put dot IC. What does that do? Is everybody cool with that? So I've just set the initial conditions so that this starts at 0 and this starts at 5. And I hit run. Let's
We put V bias N.
V bias N equals 0.
V bias N.
V bias P. Run. Can't get it to die. Let's try 1 microsecond instead. I don't want it to work. Okay, so see there, whole microsecond it hasn't started up. It's at 500 femtoamps. Let's push our luck and go to 10 microseconds. Yay, 100 microseconds. Okay, so let's hit save. Does everybody see the issue? So it's happy, sitting there for 1/10 of a millisecond, nothing's happened. This is the way it will work in the real circuit. So what I'm going to do is I'm going to add a startup circuit, which is going to trickle some current in and cause the circuit to start up. But then once it trickles in, I want the startup circuit to not influence the basic beta multiplier behavior. So look at it and tell me what you think. How can I adjust the circuit so that I trickle some current in? What's that?
Just put current source in there.
Tell me what to do. I don't know, when you say current source, my brain thinks of 3,000 different kinds of current sources. Put a diode? How about I just tell you? What I'm going to do, I'm going to copy and I'm going to put a switch here. And let's make this just a small switch. And logic, what's the minimum length for the NMOS transistors in the 1 micron process? 1 micron. Okay? So what I'm going to do, I'm going to come up here and I'm going to connect this switch. So if you haven't taken digital from me, the way you think of digital transistors is when you have a logic high on the gate, the switch is on. If the switch is on, it connects VDD to wherever I connect this node. I'm going to connect it right here. That'll definitely cause a current to flow and for the circuit to snap. Does everybody follow that? But once the circuit snaps, I want this to shut off and go to ground. The only way I can do that is if once the circuit snaps, this goes to ground, this gets pulled to ground. So what I'm going to do is I'm going to put a current mirror right here that mirrors the current that flows. And I got to be careful because I don't want a diode connects and I'll waste time because it won't work. Does everybody see that? So if it's not started up, how much current's flowing over here? None. Does everybody follow that? There's no current there's not going to be any current in here either, is there? So if I put a load here and there's no current flowing, let's just draw it and make sure you can describe this to me. If I put a load here, and I do something like this, and the circuit's not started up, how much current flows in this? And how much current flows in the resistor? None. Right? Does everybody see that? There's no current flowing in here. There's no current flowing in the resistor. What's this voltage here then? And why? It's VDD. There's no current flowing in the resistor. It means both sides of the resistor have to be at the same voltage. So what does that do to M5? The gate gets pulled to 5 volts. Turns it on. M5 starts leaking current into this diode transistor, which then causes a current to flow, which causes this to turn on. If I put a big resistor here, let's just put 10 meg, not 10 M, but 10 meg. Okay? If I put a resistor there and I hit run, look what happened. Now it's snapped. Instead of being at 500 milli, it snapped. Well, if I look at this closely, why do you think there's a lot of current flowing in this initial area here? Why is it I've got a considerable amount of current flowing right at the beginning all of a sudden? Yeah, because this guy's turning on and just dumping a ton of current into the diode connected transistor. In fact, I can go and add a plot plane. Then I can measure this voltage. And it's at 5 volts, but as it starts to turn on, the voltage drops and goes towards 0. It doesn't have to go all the way to 0. It just has to go to less than a volt or so, because this is at 1 volt, so this will shut off at 1 volt as well. So it shuts off. Does everybody follow before I finish the circuit? Because making a 10 meg integrated circuit resistor is tough.
So then M6 is turning on as M5 is turning
Yeah, so if
on?
I look at the current, here, let's just briefly save this. If I look at the current in, current in M6, I get a huge amount of current, which is when it starts turning on, but then as it turns on, M6 just goes to 16, but then if I have a huge load, it actually moves into the triode because the drain to source voltage goes to 0, because the load's pulling it down. Question? A what? Probably, yeah. Yeah. You just want to make sure that you kick-start it, so that if it's in a bad state, you say, hey, got to kick-start it, right? Kick-start my heart, right? Anybody get that reference? Really? Oh. Oh, no, all right.
I read it.
What? You didn't want to go?
No, I would have. I'm just saying I never.
Oh. All right. No, that's good. I like superfluous. Makes my brain stretch. All right. So let's fix this. I can't make a 10 meg resistor, so how do I make a big resistor? I can do it in a couple of ways. I could put a couple of diode connected PMOS there with long L's, or I'm going to try with just one. Actually, I'm going to use 2, and then we'll see. I don't remember what I did in the book, but it's probably something similar. I still remember when that student came into my office and said, I like classic rock. I listen to Blink 182. Yeah, that was about, you had to pick me up off the floor laughing on that one. Okay, so let's go. So let's go do this, and then we'll make sure it works, ask questions, and then we'll call it a day. So I'm trying to make a heavy load here. So let's copy this again. And notice my bodies of my N wells are going up to VDD. And then let's go down here, and then I need to make the load heavy, so I'm going to change this to a 10 by 10. Okay. 10 by 10. Okay, and let's see if it starts up. Save, run. And let's get rid of this plot plane so I can see things. And then, yep, starts up fine. Does everybody see that? Now let me make the startup circuit break. Let's make this go to, whoops, let's sweep VDD to something really large. Or let's make VDD go to 7 volts. Now watch what happens. I don't know if you can tell, it went up, this current went up, meaning the startup circuit's starting to leak. Anyway, we'll talk about that later. Does anybody have any questions about anything, about what we've covered? So if you ask, why to use a beta multiplier? Supply independent biasing. It generates a bias current that doesn't vary with VDD. What do you use a beta multiplier for, a BMR? You use it for setting the device sizes. That's how we set the GM, the device currents and all that with the sizes, so we can design and use the parameters in table 9.1. Okay? It's a very important circuit, so can you, over the next week, read that part of the chapter? When we come back, we'll talk about the short channel biasing using the beta multiplier, because what happens is when you have the finite output resistance, the currents still change a lot, so you have to play some tricks. And then once we get through that, we're going to talk about cascade current sources. Have a good weekend. We'll see you next Friday.